meetings. So this morning we have a great lineup of speakers, followed by the mission-driven tutorial in the afternoon. And so our first speaker is Scott Doney, and he's remote. So Scott, if you could go ahead and share your screen for slides, and I'll do it.
Okay, great. Hi, I'm Scott Doney from the University of Virginia, and I'm going to talk about some work we've been doing here at UVA and with partners at the Pacific Northwest National Lab on using an integrated assessment model to look at carbon dioxide removal. And I'm just showing here a schematic from a National Academy report of some of the different removal approaches that people have talked about, from enhanced weathering to direct air capture to blended things like bioenergy with carbon capture and sequestration. Next slide, please. So GCAM is a sort of standard integrated assessment model. It started as an energy model, an energy systems model. It's regional, so it has some spatial context around the globe. And over time, it's been connected to climate models and land surface models and water cycle models. And you can really think of it, looking on the right-hand side here, as you do need to specify some amount of economic activity, population and things like that. But what the model does is it's able to allocate resources. So for example, if you say you want to meet a particular climate target of net zero by a particular year, it will develop models of prices of different energy sources and different carbon dioxide removal sources, or prices for land, crops and things like that. And so it has a market-based system that will allocate resources to find a optimal, in the sense of low cost, solution to the constraints that you apply. And then that has impacts on the climate that can eventually feed back in. Next slide, please. So very similar to some of the work that's been done with CESM on the left-hand side, you can see the global observational temperature increase in the gray line, and then scenarios for meeting the Paris climate targets. So either staying below 2 degrees C or staying below 1.5 degrees C with overshoot. And in order to reach those climate scenarios, the integrated assessment model develops a pathway for emissions. So it's computing internal prognostically within the model the emissions of greenhouse gases in order to meet that climate target in the future. And on the right-hand side, you're seeing the, if you look at the very top, the black line would be a no policy emissions. This would be carbon dioxide emissions over the rest of the century. And in order to meet these net zero climate goals, you need a large amount of decarbonization, so a big step away from fossil fuel use with emissions, but that's in purple. Light blue is the residual emissions that the model says are too expensive, so international shipping and air travel, things like that. Also other greenhouse gases beyond CO2 in some of the model versions. And then what you end up with is the model predicts a large amount of carbon dioxide removal in the red. And just to give you a sense, the gray line with the error bars is other carbon dioxide removal estimates from other AR6 integrated assessment models. So we're well within that. We're in that ballpark of requiring a large amount of carbon dioxide removal to meet these climate targets. Next slide, please. So what does this look like? So here's just comparing primary energy use, where the left-hand panel is a no climate policy, and the right-hand panel is below 1.5 degrees Celsius with various carbon dioxide removal approaches applied. And what you see is that you have a large amount of decarbonization. You have significantly less primary energy use within these the GCAM projections. And you've also expanded, for example, the light blue shows renewables. So there's a lot more renewables in the climate target. There's a lot more dependent upon nuclear fission, and a lot more the CCS is carbon capture and sequestration. So there's a substantial amount of carbon capture and sequestration for both hydrocarbons, oil, gas, coal, but also for biomass fuels. Go to the next slide, please. And then this is showing the CO2 emissions, where on the, again, left-hand side is no climate policy, right-hand side is the 1.5 degree C target with some overshoot. And what you can see on the left-hand side, the reddish colors are CO2 emissions. The, I guess, orangish colors or pale wheat colors are the net other greenhouse gases. And then it's broken down by different sectors, for example, transportation, industry, energy, electricity, buildings. And then what you see on the right-hand panel, the things below the zero axis, the negative numbers, these are the approaches that are actually carbon dioxide removal. So in green is various different biological approaches to carbon dioxide removal. For example, bioelectricity, where you grow crops, use it for electricity production, and then capture the CO2 from that and pump it underground. So there's a net CO2 storage as part of the electricity generation. EW is enhanced rock weathering, and then the dark purple is direct air capture. And these are balanced out both globally and regionally based on resource demands and costs. So given the assumptions that the model has, the model makes a prediction about not only how much carbon dioxide removal there'll be, but how it's distributed among these different approaches. Next slide, please. So this is just showing for various different sensitivity experiments. One of the nice things about integrated assessment models is they're relatively inexpensive to run, and you can do a wide range of sensitivity experiments. The base case or reference case that we had for the below 1.5 degrees Celsius run is the top line. And then you can see a bunch of different sensitivity runs. For example, the second line down, high cost CCS is saying, well, what if carbon capture and sequestration is really expensive? How would the model respond to that? Or limited biomass would be, what if policies were put in place to limit how much land could be used for example, for bioenergy crops? Next slide, please. And one of the nice things, and I think connects to the working group, is, some of the integrated assessment models like GCAM have spatial resolution. So a lot of the land surface processes and water cycle processes within GCAM are done at the large river watershed basin. So all the different, you can see the watersheds there in the plot. And one of the things you can look at, for example, is as an impact is if the model is suggesting you need a lot of bioenergy with carbon capture and sequestration, you can compare those bioenergy crops to how much cropland is available in each of these watersheds. And you can see that the model's predicting, at least for this scenario, without some external constraint, the bioenergy crops would use up a large fraction of the cropland, displacing crops used for direct human feed or for animal feed. So you can start looking at these trade-offs and impacts. You can also look at fertilizer use, water use, things like that, primary energy demand for carbon dioxide removal. Next slide, please. We've also done some work, and this is the work of a graduate student here at UVA. There are versions of GCAM that resolve at the individual state level within the US. And this is showing for the same type of scenario, how if you had a national goal of meeting net zero by mid-century, how different the behavior, economic factors might be in Texas and California, where Texas has a lot of opportunities for renewable energy and geologic carbon sequestration versus California, which is not able, doesn't have those many of those same opportunities. While California here isn't balancing its emissions, it doesn't reach net zero. It does contribute to an overall national net zero emissions goal. And so you can start looking at the economic and political and social factors that might play in as different states respond to national climate goals. Next slide, please. And then, of course, you can hear digging down. This is looking at a variety of different impacts for the same national goal at the state level. So it goes from final energy consumed by carbon dioxide removal, fresh water consumed, forest land growth, croplands, and biochar. And so I think there's a lot of potential connections between what we're doing in the integrated assessment space and what's being done in CSM as we're developing different scenarios for thinking about carbon dioxide removal. And then the next slide, and I think this is my last slide. I just wanted to say that, you know, one of the, if you think about CSM as focusing at the sort of 9 o'clock, if you think that as a clock face, the geophysical feasibility of these CDR approaches, I think bridging between CSM and integrated assessment models allows you to look at, in addition to geophysical feasibility and perhaps environmental feasibility, you can put in constraints and model things like technology, economic, and then also connect into social and cultural feasibility. So I'll stop there, and I think I have a minute or two left for questions.
I couldn't really hear you then.
Yeah, I can hear you fine, Rosie.
Okay, cool. Yeah, this is a really interesting space, how land surface models can inform IAMs, and there's a lot of work on this in Europe, which isn't normally focused on GCAM, but it's instead quite a lot focused on the kind of magpie remind system.
Right.
But the logic is similar, and so I just wanted to kind of, I guess, do a little shout out to we had this European project where we ran a bunch of simulations to look at the output of like CLM and Jules and Orchid and JSpark under a bunch of different scenarios to see how, you know, to kind of look at the feasibility of bioenergy and forest carbon storage and like reforestation, and the idea being that all of those would inform the uncertainty inside of the IAM, right? Mm-hmm. And so we kind of have them sitting around, and if anyone wants to kind of think about maybe using that output in the context of GCAM, that will be fun. Anna Harper is probably the main person who's kind of working on those right now. She's just moved to Georgia. So yeah, we have a lot of, we have a bunch of new projects starting up on this as well, thinking about how to link uncertainty in Earth system models into IAMs. So it'd be fun to think about how this applies across different IAMs, because they're all, our ones are all very European focused.
Excellent.
Is there another question? Yeah.
I see Joshua has raised their hand.
Okay, go ahead, Joshua.
Yeah, so my understanding is that most integrated assessment models sort of function on economic units, which don't necessarily have like a mapped to the globe spatial representation. And you were talking about some of these economic processes, and I know that they represent things like where crops are produced and things like that. But when it comes to BECCS, there's constraints related to geological reservoirs where you can store things. Have those been worked into the model so that the model can calculate economic costs, or do you have to sort of just basically say, give them those scenarios of high versus low to do the scenarios, or can it calculate those economic costs of some of these advanced technologies themselves?
Yeah, so GCAM is computed at political units. So some of them are countries, but some of them are like, you know, the EU is a political unit, and different IAMs take different approaches to that. We do try to look in, for example, with geologic storage or enhanced rock weathering. We do sort of try to look at resource locations and transportation costs. So you can factor in, for example, when we did the GCAM USA, we were looking at, enhanced rock weathering. It's really expensive to mine bulk rock and move it. So we put in costs for transportation. So the further away you got from source regions or sink regions, there's a very good database, at least for the US, from USGS, on where you have geologic sequestration resources in the sense of places for CO2 to be injected. And that is factored in terms of, you put a cost for transporting CO2 long distances, and it makes it less favorable. And that was why, for example, Texas looked very different from California, because Texas has a lot of localized geologic sequestration. That's all stuff that needs to be, be refined over time. But yeah, that is built into the model.
Thank you.
Okay.
Cool.
I think maybe we'll go on to our next speaker. Thanks, Scott. That's great. Next speaker is Jinmu Liu. Are you online?
Hi, I'm here. So, good morning, good afternoon, and good evening, everyone. My name is Jim Wu. I'm a third-year PhD student at Cornell University. So today I'm going to talk about my research about the constraint of the denitrification and leaching in the CLM 5.1. So here, just like a little bit of background about the nitrogen cycle. I guess this plot gives the major pathways of the nitrogen cycle in your terrestrial existence. So as you can see, so the major nitrogen input is from the nitrogen fixation and also the fertilization and subject fertilization. These are two very important nitrogen input to the whole soil system. The other sources like nitrogen deposition, they are not very huge, but actually still maybe very important regionally. As one of the basic nutrient in the Earth system, nitrogen can release from the soil only two major pathways for nitrogen leaving the soil: leaching and the denitrification. The first pathway, leaching, is happen in aqueous phase, which means that water is driving the nitrogen out of soil, and denitrification is second one, which is just like the bacteria turn nitrogen in the soil back to the atmosphere in a gas phase. So what's the problem they have? My studies want to just figuring out of fluxes about denitrification and leaching. So to identify issue in the Earth system model, just like first one is overestimating denitrification, and the second one is a small leaching compared to a small leaching problem. So there are many research about these two topics, but today I'm only bring one. So Fan et al. 2022, he compared isotope benchmarking research and their infer from this isotope benchmarking budgets. He found that in a certain Earth system model in the CMAP6, almost all of them overestimate denitrification by a factor of almost 2. So as you can see from the graph here on the left, so the first part is the isotope benchmarking budget, and the second part is the CMAP6 based budget. So the blue bars is the leaching flux size, and the pink bar is the denitrification flux size. As you can see, compared to the isotope benchmarking, the Earth system estimated denitrification is very small, and the denitrification is very huge, and leaching is very small in the Earth system model. So here, just like for simplification, we bring you a ratio, just like here. We define ratio leaching over denitrification. So Earth system model estimate this ratio is really as about 0.3, but isotope benchmarking suggests it should be around 1.4. So there's a huge difference between them. But actually, I should remind you here, this isotope benchmarking is only compared over the forest soil. It's really not a global budget, but I still give some highlight of the difference between the denitrification leaching estimate in the Earth system model. So here, this is a global spatial distribution of fraction of nitrification and losses simulated by CSM2 in the right graph. As you can see, in most of the places, the CSM2 predicts nitrification is the major loss pathway for soil nitrogen. Only in the Western US, leaching is important, but isotope benchmarking suggests a total different story. So in our study, we developed a model called flood of agricultural nitrogen. So this model is designed to help to extend the nitrogen cycle in a CLM. Also, this model want to help to improve CLM modeling in several aspects, like volatilization of ammonia. So we can take advantage of this model to discard different nitrogen issue in the CLM. So we really hope to investigate the nitrogen process in the CLM. So our co-author, Stephen J. Hall from University of Wisconsin, he provided us with this local site mesocausal measurement. This measurement set us to investigate nitrogen dynamics under different fertilization experiments. So in the many observations it provided, the most important one is the leaching. It can provide carbon leaching over one place, just as you can see from the B graph and D graph. It can collect the leaching under the column. So this observation is really helpful in evaluating the CLM leaching. But unfortunately, this observation couldn't provide a denitrification flux size. It is very hard to observe. And in order to compare with evaluating CLM, the first thing we need to set out a single column CLM model combining with our FAM model. So several modifications have been made on the CLM listing single column model. Just for example, the first way you should guarantee this observation and the model has the same climate forcing, like a precipitation temperature. And the second thing that's like I need to change. I also need to guarantee the single column model has the same soil property, just like a bank density as this agriculture site. And also I want to change the fertilization amount, time, and location. I also want to change one of the most sensitive parameter in the model is the planting day, which is very important to the nitrogen dynamics. So here's the primary result I obtained by comparing the CLM 5.1 default model with the mesocosm observation. So as you can see in this graph, the x-axis is the different fertilization experiments. Just the fertilization experiment increases from 12.3 to 21.3, and the y-axis is the accumulated nitrate drainage over the whole year. There's a yearly accumulated drainage, a nitrate drainage. So these bars are the measurement from the mesocosm for two different soil, Clary and Webster, and the gray stars are the measurement the simulation from CLM 5.4. As you can see, CLM 5.1 predicts small leaching for 2022. Even the 2022 was a high leaching year. And also, I want remember that we have matched many things in the CLM with this observation site, just like a fertilization amount, precipitation, temperature, soil property. But so it is still surprising to see that CLM still predicts such low leaching. So there's maybe something very important in the CLM to cut this problem. And what's the problem? So I use these two plots to just kind of describe the problem CLM has. Just like you can image that these two are the soil columns. So here is the land surface. Vertically is the soil depth. So the red one is CLM default, and the green one is our new proposal. So let's go over how CLM calculated nitrate leaching. So first, CLM assume nitrogen doesn't move with water vertically. That means that it remains at a fixed profile here, like I plot, and CLM predicts the total water drainage here. But CLM will redistribute this water drainage back to layer by layer based on the soil moisture information, and then nitrogen leaching is finally evaluated in different layers from this redistributed drained water. So that could be a problem from the for this simple scheme, just as I plot in this graph, right? if most of water stays at the bottom of the column, even you have larger water drainage, but the total nitrogen leaching could be very small just because your nitrogen doesn't move with water. Water can just move down. So in order to solve this problem, so we develop new methods in our model, just like nitrogen should moves downward with soil water, and leached nitrogen is taken out at the bottom of the column as I show here. In order to do this, what we need to do is just solve this one-dimensional continuity equation in a CLM. So here's just like the result I obtained after I incorporated my methods into a CLM. The left panel is the y-axis is the time temporal, and x-axis the time temporal, and y is the soil depth. It starts from 0 to 3 meter depth. So yellow colors are the nitrogen concentration. So as you can see, in the CRM 5.1 default, the nitrogen doesn't move with the time, right? It stays at the same places across the whole time. After incorporating our simple method into CLM, the nitrogen begins to move down, especially for the high leaching year. So finally, we can just obtain a real nitrogen drainage at the bottom of the soil column. And let me bring you back to the plot, bar plot. So after we incorporating the method, what's the performance of our new model? So here again, the x-axis is the different fertilization experiment, and the y-axis is the nitrate total drainage over the 2022. So CLM 5.1 still performs not good, but actually after incorporating our method, just like as indicated by the pink and the green diamonds, we have better performance than CLM 5.1. That's much better. And actually, we show the gradients between the different fertilization amount. So this is really interesting methods. And we also found very interesting, like a different initial saline density could affect the leaching a little bit. So I have talked a lot about the leaching. So how we solve the denitrification problem in the CLM, because we remember that there's an overestimated denitrification problem in a CLM, but unfortunately, we don't have any observation available to let us to investigate this problem. So instead, we just check out the model structure, and we found there's one maybe important function in the denitrification module in the CLM could cause this problem. So the CLM 5.1 uses the anaerobic fraction, and we found an alternative solution called based on the WFPAs. So this graph plots the denitrification against the WFPAs. X-axis the different WFPAs start increase from 0 to 100, and the y-axis is the denitrification rate. So as you can see, the green pluses are from CLM 5.1 default, and our new simulation is other yellow dots. So our new methods can largely reduce the denitrification in a moderate water field porosity space, but actually it's not just only scaled down, but in the high WFPAs, we still have a high denitrification potential. So that means this alternative method can partially help to improve the problem of overestimation of denitrification flux in the CLM. So finally, I'm gonna bring you to this stimulating nitrogen budgets. There are too many numbers. What we need to focus today is the denitrification here and the leaching here. So I use this simple table to summarize what we have done for the CLM. It's like again, this is leaching over the denitrification ratio. So we increase this ratio from CM 5.1 default from 0.014 to 1.7, which is this is really small, and right now it has the value of 1.7. And the isotope we are more close to the isotope benchmarking suggestion, but actually again, this is the only model adjusted by one single agriculture site. So I'm not sure what about global budgets, and I haven't run a global simulation because of the spin up problem. I think I have run out of time, so I'm gonna put my conclusion here, and I'm glad to take any questions. Thank you.
Thank you, Jen. Any questions? Well, I don't know if we have a lot of time. Maybe one question.
That's a good question.
Okay.
Jimmy, this is exciting to see. Did you have to change anything with the nitrification? At least my sense is that CLM5 also has really low nitrification rates, and it looks like you're somehow getting much higher nitrification rates, and I'm wondering if you had to do something to
Yeah. So sorry, I haven't introduced all of my modification on this new model because we don't have time. Sorry. So definitely for the nitrification, flux is very small. Because there's one threshold in the CLM model. They say only 10% of an ammonia is available to be nitrified per day. I think there's some research say this ratio may be too small. So in our new model, we increase this threshold to 50% based on the observation of the inorganic concentration. So finally, you can see here this number increased a lot because we just higher the threshold. This is a very simple solution. Yeah.
Okay, cool. Thanks.
Okay.
Thank you. So next up we have Leon Lei online.
Good morning, everyone. My name is Lian Lei, and I'm the first year PhD student at Charman University, and I'm so excited to present our recent work, a tropical and decadal scale CO2 fertilization and using new data for one of the largest model uncertainties. Uncertainties in CO2 fertilization effects on global carbon uptake are still dominated by the tropical response. But however, most phase experiments have been conducted outside the tropics, leaving a major gap in model validation. And to address this, a long-term CO2 fertilization data from tropical regions are needed. And today, first, I will introduce the Elevate project, which provides a unique natural experiment for studying CO2 fertilization effects in tropical forests. And then I will present our efforts in integrating Elevate data into CLM5 and focusing on ET regulation and future climate projections. And so first, what is the Elevate? The Elevate project was initiated by NASA JPL to investigate the interaction between Costa Rica's tropical forests and its volcanic systems. And one of the key findings was that many phonoleric vents scattered across the region emit elevated CO2 concentration with little or no other gas emissions. And this provides us with a natural long-time CO2 fertilization experiment. And there are three key advantages. The first is, unlike the short-term phase experiments, it is decadal scale exposure. And the second is it is a larger affected area is much bigger than other traditional phase plots. And the third is it is true tropical conditions addressing a major gap in current studies. And so the Elevate data, the upper left two photos shows a vent in the middle of the rainforest emitting CO2 at more than 1,000 ppm CO2 concentration. And the panel B shows the tree canopy structure in elevated CO2. Around the vent, the canopy level mean CO2 is much higher than other areas. And moreover, the geological CO2 source has a distinct isotopic signature, which allows us to track the CO2 exposure at an individual tree level over both space and time. And CO2 fertilization affect tropical ecosystem structure, composition, and functions. And elevated CO2 has higher biomass, stain density, and GVP, and water use efficiency than other ambient CO2 conditions. So why the Elevate important for Earth system model? Elevate is important for Earth system model because it helps reduce uncertainty in carbon climate feedbacks. Specifically, enables us to study how tropical forests respond to CO2 enrichment in real-world conditions. So for this presentation, I focus on a volcano in Costa Rica, where we indicate eco-stress observations into CLM5 to better capture the ecosystem responses to elevated CO2. And one of the key mechanisms we explore is how evapotranspiration regulates carbon and water dynamics on the CO2 fertilization. So we know that the CO2 fertilization affects both carbon and water cycles, but how does ET mediate the interaction? The key factor here is stomata conductance. The higher CO2 concentration leads to lower stomata conductance, meaning that the tree reduces the water loss while still maintaining the carbon uptake. And ET served as a critical link between carbon and water fluxes, making it essential to accurately represent eating models. And so our goal was to improve the representation of ET in CRM5 by integrating elevated field observations. So to achieve this, we introduced a scale adjustment alpha to the stomata conductance equation, modifying its sensitivities to CO2, and which help reduce the model biases. And we integrated it into CRM5 first, and then FATE, and eventually to the CESM. And for the results of the model validation, incorporating elevate constraint data significantly improved the CRM5 performance, resulting in a higher R-square value than the original CRM5. This increases confidence in the model's ability to simulate tropical CO2 concentration, CO2 fertilization effects. And I also want to know the relationship between CO2 concentrations, VPD, GS, and ET. And I use hourly daytime data. The output, I observed the ET increases with canopy VPD when VPD is smaller than 5. And EQD then decreases with VPD when VPD is larger than 5. And stomata conductance decreases with increasing CO2 concentration. And this is consistent with theoretical expectations. So this finding suggests the ET responses to CO2 enrichment are nonlinear, with stronger regulator occurring under high BPD conditions. And we also analyze the variation over the year under CO2 fertilization and find the elevated CO2 results in a slight increase in surface temperature with an average rise of about 0.05 Celsius degree. And stomata conductance significantly decreases under elevated CO2, reflecting reduced stomata conductance opening due to the higher CO2 availability. This reduction leads to a decrease in ET, though the change is moderate. And conversely, the GBP shows a large increase under the elevated CO2 with an annual rate of about 300, and driven by the enhanced photosynthetic activity. And this result highlights the interplay between CO2 levels and plant water carbon dynamic, emphasizing the importance of accounting for stomata conductance sensitivity in climatic situations. And we further examined the future climate projection under the different SSP using data from 5 ESMs. The result indicated the stomata conductance decrease in SSP 370 and SSP 585 compared to SSP 126. And ET follows the order. SSP 585 is larger than 370 and larger than 126. And GBP, but the GBP differences are not significant. And it maybe it's an uncertainty in carbon uptake responses. And water use efficiency is highest in SSP 126, while the soil moisture is lowest in 585, indicating the potential risk for tropical ecosystem sustainability. These results are under the base CO2 concentration, and next step I will consider a changing CO2 concentration next under different SSP scenarios. So for the future study, we aim to expand our data set to integrating such as the soil carbon and nitrogen data, and leaf and canopy nutrient trace, and soil and steam and respiration measurement, and leaf level gas exchange parameters, and also the high resolution remote sensing data set. And additional, we plan to incorporate CRM5 phase and CESM for improving the tropical carbon climate feedback simulations. Thank you.
Questions for the Yeah, this is really interesting to see. It seems really consistent with what we're finding when we run global CESM with changes in the Medellin slope, which is essentially what you've done by adding a scaling factor on the CO2. So I was wondering, how can you untangle just like knowledge of what the G1M slope should be for these trees versus it actually being, or is that just what this is, right? A local difference in the G1M, or a difference in what we think G1M should be for these trees?
Thank you for question. You mean the tree levels, or sorry, could you repeat your question?
Well, putting a scalar on the equipment, I can get into the details later, but yeah, basically, like, do you think this is basically a correction on what we know about trees in general, or is this something specific to the adaptation of these trees local to this high CO2 source?
Yes, so for the model, first, in this stage, I use the equation to the grid level, and so in Elevate project, we also collect the tree level data, and so maybe we can consider the tree level or then the soil data.
Thanks.
Okay. Thank you.
Any more questions online?
Are there any questions? It's just been chat with Jimmy.
Can go on to the next speaker then. This team.
The last 2 years, I've been working with Kevin Schaefer, also at NSIDC, using the Subcasa model, and we've been adding mercury to it to make global scale simulations of the mercury cycle. So I know mercury is a little bit of a different topic for this modeling community, but just to provide a bit of context, mercury is one of the United Nations top 10 chemicals that endanger human health and the environment. So since the Industrial Revolution and even before then, humans have enriched the amount of mercury that's present cycling around the Earth by a factor of 3 to 5 in the land, ocean, and atmosphere. So this has shown up in different problems at different times across the world. For my dissertation studies, I have a special interest in permafrost mercury because scientists in the last 10 years have discovered that there is this vast reservoir of mercury in permafrost. So one of the questions that I'm trying to answer with adding it to Subcasa is how much, when, and where this mercury is going to go. But anyways, today I'm just going to show you a little bit more different research question, which I'll get into in a moment. So for those who are in the mercury research community, mercury does bind to organic matter. So thus the terrestrial carbon cycle modulates the global mercury cycle. So we see a lot of like the same processes of like deposition and evasion and runoff that tend to follow carbon. So thus in Subcasa, we're able to use carbon as a proxy for mercury cycling. And this graph here on the bottom right just shows this positive correlation that we often see between mercury and carbon. These are like soil cores from across the US. So we have fully coupled now the mercury cycle with the carbon, water, and energy cycles in Subcasa. And for those who aren't familiar, it's the simple biosphere Carnegie Ames approach model. It was a model that was developed in the mid-90s and it has been kind of progressed over the years. But here I'm showing just like the key processes of mercury fluxes that I've included in Subcasa. And again, a lot of the same ones that you see for carbon. So I have photosynthetic uptake, respiration, root uptake, soil and water cycling processes, wet and dry deposition, and then runoff to lakes and rivers. So the question I'm going to ask today is, how will mercury fluxes respond to environmental factors such as temperature, soil moisture, and other meteorological drivers at a global scale? So for this presentation, I conducted global simulations from 1901 to 2021 at half-degree resolution forced with CRUNCEP data. And so we're going to move on pretty quickly right into results. So these are relative standard deviations with regard to a reference value, which I'm going to show for each of these fluxes. But I'm looking at both evasion and uptake in these next couple plots to see how different climate parameters impact mercury fluxes. So as you can see here in the top for evasion, the blues and the greens, that means that temperature has a stronger impact on evasion. And I should mention that evasion is basically a good proxy for respiration, and then uptake would be photosynthetic uptake of mercury by plants. So as you can see, especially in the northern latitude where it's frozen a lot of the time of the year, once those soils and that ecosystem finally warms up, temperature has a big impact on mercury uptake in these ecosystems, which we do see in the literature as well in the field. And then here in the lower graph, not as much of an impact on uptake, but still we do see this strong spatial variability by temperature. So here in this next graph, I'm showing you soil moisture and how that impacts mercury fluxes. So we see now kind of a shift of like the blues and the greens now to the mid latitude and the drier climates. And we would actually expect this. This is good to see because as soils dry out, mercury isn't able to bond to organic matter as well. So it becomes more susceptible to volatilization processes and then this emission that we see. And then because photosynthesis is sensitive to like humidity and light, we wanted to look at that as well here. For these graphs, I'm just showing mercury uptake. And so not a huge response at the global scale. It is a bit weak, but we do see a little bit of a signal around the tropics in places where you tend to have more cloud cover. So those areas are a little bit more sensitive to light as far as photosynthetic uptake of mercury. So that's all I have for now, but hopefully I've made clear the point that the terrestrial biosphere does modulate the global mercury cycle. To date, we only know of 3 other models that have included mercury at a global scale. I think there is a group now that has added it to the CLM model. We think, though, that ours is still the most advanced terrestrial land mercury model, but we have yet to be contested. But with that, I'll take any questions, and thanks for your time.
Okay, any questions for Christine? Gretchen.
I'm just interested in the first statement you made about how there's a big reservoir of mercury in permafrost. Can you tell us about that?
Sure, yeah. So because the northern hemisphere has very organic matter-rich ecosystems, like permafrost has a lot of carbon and organic matter. It's basically like a big sponge for mercury that's been emitted from mid-latitudes for the last couple hundred years. And then because of just like the cold, dark climate a lot of times of the year, we don't see much re-emission of mercury like we do in other places of the globe. So it has become this sort of storage pool over time.
Thanks for your talk. You mentioned mercury kind of follows carbon. Could we expect it to like respond similarly to global changes then as we expect carbon, or is there kind of different processes going on?
Yeah, so what we're thinking is 2 big pathways that we're going to see change is CO2 respiration, and also in that process with microbial decomposition, they do interact with mercury. So there is a mercury evasion from microbial respiration, and then also just from organic matter decomposition, like abiotically, and then dissolution to like, soil, water, and like rivers and oceans. That is another big area that we're looking at. So we're trying to see exactly how much is going to be partitioning glucose pathway.
Any more questions, other questions online?
I have a question. I don't know anything about the mercury cycle, but I feel like at least my intuition is that the hydrologic losses are I think a bigger deal. And maybe that's just because that's where I think I had no idea that it could have paid from soils as a gaseous form. That's kind of terrifying. But I guess I'm curious if this coupling of mercury and carbon works for like the terrestrial biosphere, but it maybe has different, like if the hydrologic pathways are more important, that would be I guess a decoupling of carbon and mercury.
Possibly, yeah.
Or do you know like how much of it's lost out the bottom versus the top?
Depends, I think, on like what ecosystem you're in. And I know that plants, like plant uptake is it plays a very big role in retention.
Yeah.
So it really kind of depends, I think, on like the quality of carbon in that area that you're interested in, as far as like whether hydrology or carbon is going to play a bigger role. Yeah, sorry, not a good answer.
Yeah.
It's kind of
Well, I guess I was just kind of like thinking of the denitrification talk that we just heard, and like if it's actually it's kind of in some ways cycles more closely to nitrogen in terms of the partitioning of hydrologic versus gaseous losses.
Yeah.
Yeah, it's cool.
This is interesting to think about, and somebody at my university is working on how mercury might be impacting photosynthesis. Is that something I didn't quite catch? Like, what are the assumptions about that? How much do we know about it? You know, how can we couple it in not only to like the fact that it's bound to the carbon moving around the carbon, but that it will influence the rates of carbon uptake as well?
Yeah, so yeah, there's definitely a correlation between kind of like photosynthesis and then uptake. And so I guess whatever the plants are doing, you know, if they're in an environment suddenly it becomes more stressed, we could expect there being less mercury uptake. And
This was more about like damage from the mercury
Oh,
to the
damage.
to the photosynthetic machinery.
Yeah, that we have seen evidence of that in some. I have seen some case studies where that occurs, like I think in the Amazon, especially there's a lot of high amount for mining. But I haven't seen it too often. Maybe, yeah. I would say that on a global scale, it probably isn't going to have a big impact, but maybe localized where there's hotspots, it could.
Any more questions? All right. Next up, we have Katie Rossi.
Okay, good. Okay, great. All right. So I'm Katie Rossi. I'm a postdoc with Will at CU, and then also with Peter Reich at University of Michigan, and then also a long-term visitor here at NCAR. So I don't think I probably need to tell this group that global changes like elevated CO2 and warming aren't happening in isolation, right? They're all happening at the same time. And when we use representative concentration pathways in our models, they're allowed to kind of feed back, right? With the climate system, we get kind of warming and elevated CO2 and all these things happening at the same time. But when we do these experiments out in the real world, they require immense amounts of infrastructure. And so this is a free air carbon dioxide enrichment experiment or a FACE experiment. You can see that there's huge amount of infrastructure to try to elevate CO2 in this forest. And so running these experiments is very expensive and difficult. And so we don't have a lot of them. So to kind of get around this problem, over 20 years ago now, Norby and Luo suggested that we gain a really thorough understanding of single global change factors. And then we put those into models and use those to understand interactions of global changes. But even they acknowledge, right, that these multi-factor experiments where you're doing multiple global changes at once remain important because there might be surprises, right, where these interactions don't happen as we'd expect. And in fact, these surprises might be more common than we think. So my other postdoc advisor, Peter Reich, published this paper back in 2020. And I'm just going to read this line from the abstract here. They find that multiple global change drivers had a profound combined influence on observed outcomes that would have been poorly predicted by the knowledge of each driver alone. And so this to me begs the question, are you representing interactive effects of global changes well in land models? And then if not, what are the mechanisms needed to represent these interactive effects well? And so to that end, we're taking advantage of a multi-factor global change experiment called Terracon. This is done up in Cedar Creek, which is a tall grass prairie up in Minnesota, and it's been happening since 2012. And they have 4 different global change factors here. So they elevate temperature using these heat lamps above ground, and then also have cables below ground to elevate soil temperature. They do rainfall reduction with these like tent-like structures they put on plots. And I learned last week this is event-based rainfall reduction. So someone has to go out every time it rains and put these up, which I'm assuming in Minnesota is a lot of rain. So that's, you know, a lot of work for somebody. They elevate CO2 using these PVC pipes. And they just pipe in more CO2. And then finally, they do nitrogen addition just by fertilizing the plots once a year. And so this project focuses on the temperature, the elevated CO2 effects. Okay, so I'm going to show you some observational data now. So this is after 10 years of the experiment. It seems that carbon cycle responses indicate interactions between elevated CO2 and warming, and that those interactions are influenced by nitrogen availability. Okay, so I'm going to show you a series of plots like this. So they're showing you responses of carbon pools to elevated CO2. And so if the bars are above 0, they're responding positively. The bars are below 0, they're responding negatively. The x-axis is the temperature treatment, so ambient and then elevated temperature. And then the color is the nitrogen treatment. And so what you'll see for leaf carbon in this kind of orange box here is that leaf carbon responds similarly to elevated CO2 and temperature, regardless of nitrogen availability. But if we move on to soil carbon, we see opposing responses depending on nitrogen availability. And so what this means to me is like a soil biogeochemist potentially. Carbon in soil is stored in soil organic matter, which also stores nitrogen. And so potentially when nitrogen is limiting in this ambient nitrogen situation, you might break down that soil organic matter to get nitrogen. And so that could be kind of driving these opposing effects. And then we see similar opposing effects with root carbon. And so this could be, you know, a change in root allocation perhaps that is allowing for more nitrogen uptake by the plants. And so if you didn't quite follow that kind of soil biogeochemistry deep dive, the important thing here is that soil biogeochemistry might be driving these responses. And to that end, we want to assess whether soil biogeochemistry alters responses to interactive global change. And so we intend to use CLM5 with its default soil model, which is a century-like soil model that I'll refer to as CLM default. And then we also will use CLM with Mimics, which is a soil model that Will and others developed that represents kind of more novel understanding of soil organic matter, and so might kind of have different responses under interactive global change. And I should say that I'm pretty early on this project, so I'll only be showing you CLM default results today, and I'm very happy to hear feedback and comments about this work. Yep, so we'll have those 2 models. We'll run them under a control scenario, which we'll use for calibration, and then we'll run them under warming, elevated CO2, and the interaction. Okay, so first, to parameterize the model, we first just updated the model with observed plant traits and soil properties. And then Linnea helped me adapt TPE tools for a single point simulation. And so we use those to parameterize the model. And I want to say that first to thank Linnea and the PPE team, but also because we have these kind of single point tools in case they're helpful for anyone else. But this is what we get from out of the box model with updated plant traits and soil properties. You can see we're overestimating shoot carbon a little bit, underestimating root carbon, and overestimating soil carbon. And so we increase soil carbon decomposition rate and change the root distribution to kind of fix this. I put the parameters on there in case anyone cares. I think if anyone's going to care, it's maybe someone in this room. So put those up there. And so when we change the model in that way, we get the orange points. And so you see that we actually don't change shoot carbon very much, but we do improve root carbon, and then soil carbon is a lot better. So sorry, that's a 1-to-1 line there. And so that's where we're starting from for our global change experiments. Okay, so we run those, and I'm going to show you a series of plots like this that are various carbon pools on the y-axis, and then the time of the experiment on the x-axis. And there's a lot of things we could look at. I'm going to show you observed results too and compare them, and there's a lot of things we could compare about them, but what I want to focus on is the interactions. And so that's what we're going to focus on. The blue lines will be the control. The orange is warming, green is elevated CO2, and red is the interaction. So if we start from the control, we see that elevated CO2 increases shoot carbon, warming decreases shoot carbon, and then the interaction is right in the middle. And so when we are able to predict the interaction from the individual effects, we call that an additive global change effect, because you can just add those two responses together to get the interactive response. But then if we look at observations, first you'll note that they're messier, right? Which is not surprising, I think, to probably anyone. But if we focus on the kind of last few years of the observations, what we see is that warming and elevated CO2 don't really have an effect on shoot carbon. But despite that, the interaction increases shoot carbon, right? And so because that interaction couldn't be predicted from the individual factors, we call that a synergistic interaction. So not the same, right? Okay, so moving on to root carbon. So we see again that elevated CO2 increases root carbon. Warming doesn't really have an effect here. And so the interactive effect is the same as the elevated CO2 effect. And so again, this is an additive effect. But if we go to the observations, again, focusing on the last kind of few years of data here, we see that warming increases root carbon stock, and elevated CO2 slightly decreases root carbon stock, but their interaction strongly reduces root carbon stock. And so again, this is a synergistic effect, right? We can't predict this interaction from the individual effects. And so you might be noticing a pattern here. We'll continue the pattern for soil carbon. And so for soil carbon, again, we see elevated CO2 increasing soil carbon, warming decreasing soil carbon, and the interaction being in the middle. So again, an additive effect. And then for the observations, we don't take these observations as often because soil carbon doesn't change as fast as plant carbon. But what you'll notice is that elevated CO2 and warming both increase soil carbon in this most recent sampling, but the interaction actually decreases it. So again, not be able to predict that interactive effect from these individual effects. And so, right, why does this matter? So this is kind of going back right to that Norby and Luo idea, right? That if we put these single factors into models, then we can look at the interaction in models, but we're actually not predicting the interaction very well. And so maybe we need to use our observed data to work on interactions in the model. And because of my interest in soil biogeochemistry, I'm interested in whether soil biogeochemistry is a factor in this. And so the next steps are then for the different representation of soil biogeochemistry show kind of more aligned global change effects. And we might expect this to happen with mimics because mimics has this explicit representation of microbial biomass. And because of that, it can better represent these priming effects in soil. And so these are these effects when you have more plant input, you generally break down more soil organic matter to get things like nitrogen. And so that might be better represented in mimics than in the default CLM model, soil model. And then beyond that, if mimics still doesn't get us there, the next question is like, what other processes might need to be represented in CLM that are not currently to get these interactions right? And so we published a paper last year, which did kind of a toy attempt at this, where we looked at the response ratio of various pools and mimics to elevated CO2. And you have to look at this whole plot and understand it, but I just want to point out that when we change the amount of plant allocation through exudates, it changes the response of this soil organic matter pool to elevated CO2. And so this is just an example of something that might need to be represented in CLM to get these interactions right. And I should say this is also just one site, right? And so we don't know if these interactions are necessarily always synergistic. So I just want to say that. But yeah, that's all I have. Thanks so much for listening, and I'll take any questions or comments.
Questions for Kate? So in the literature review, you mentioned that sometimes some climate change drivers like coupled effects that are more than the sum of their parts, right? But then it didn't necessarily seem like that's what you experienced with the warming and the CO2. You said it was more like an additive effect. Is that kind of what you expected? And then kind of, I guess, what isn't additive per se? Like what effects might kind of, couple?
Yeah, so I think the model was certainly showing additive effects, and that's maybe what we'd expect, right? If we have, I guess I don't know CLM's like history of comparing global change experiments, but I maybe assume that they've mostly been single factor global change experiments. And so the additive is maybe what we'd expect CLM to do. But the observations don't necessarily show that. And I will say that other sites, so there's not that many of these like interactive global change experiments. And I will say that another quite famous one, Jasper Ridge in California, shows more of these additive effects. And so it could be something about this R site that is unique. But we don't have enough of these experiments to really have a great like broad understanding of that.
Yeah, so how are you deciding whether the observations are, because they're looking pretty noisy, like you're seeing the signal change from year to year, and so yeah, what you'll focus on last year, but
Yeah, I mean, we can average across years, and it's a pretty similar response. But you're right that like the error bars are pretty big there, right? And
the order changed as well.
And the temperature one, the order flipped, right?
The temperature when the order flipped.
The temperature was lower.
Oh, like the responses to, well, but like that being said, like we don't necessarily expect that all the carbon pulls will go the same direction, right? Like I think like that's like you might think that, right? Because plant input might lead to more soil carbon storage, but if those plants also need more nitrogen, it might break down that soil carbon. And this kind of response, of these opposing responses of below ground and above ground, have been shown at the global scale too. So that itself is not too surprising to me and might be more robust. But I think Dave's question is a fair one, that the observations are quite messy. And so we can think about the limitations of this, but yeah, I think, is it applicable more broadly? I'm not so sure. I think we don't have the observational data maybe to say if it's applicable more broadly. So it's maybe more of like a test of theory here, right? That like these additive effects aren't necessarily always to be expected.
What are the bars? Are they replicates or are they?
Yeah, they have standard error on the replicates. Yeah, there's only like 3 or 4 replicates.
There's probably also observational measurement error.
Sure. Yeah, that's part of it too, I'm sure. Yeah.
So I'm just kind of curious. Like I think at least I've conceptualized the PPE as like putting us in like different spaces in terms of the response that the global model might have to elevated CO2, for example. And I wonder, I guess I'm curious with the PPE work that you've done. And I realize this is like hot off the presses, but like, is it like before we throw the model out to say like, oh, the model's always additive and we only get these additive effects from the model, which might be true. But I guess I'm curious if like there's different parameter calibrations that we could think about using from the PPE work that you've done, even if they don't give you as good a match with the observations, if they would at least put us in a non-additive or a synergistic space.
Yeah.
Or if it's like structural underpinnings of the model, like, changed in allocation or something.
Yeah, yeah, that's a good point. I think we could probably try both. Like I had like the root allocation example, but
Yeah.
it's probably easier honestly to change parameters than to actually change the model. And so maybe that's like a better way to go after seeing how Mimics does. Yeah.
Any more questions? We have none online. So now it's just discussion. So I don't know if anybody has any discussion topics to bring up after the talks this morning.
This is maybe more of a comment. I feel like I've gone to biogeochemistry sessions in the past and been like so envious that the ocean gets to think about more than carbon and nitrogen. So thanks for adding new elements to our table. We can think about.
Yeah, we have a lot of nutrients.
I know you guys get to do like have the whole periodic table at your disposal.
Well.
The relevant stuff.
I'm a little curious about the thinking about the sort of natural experiment we saw with the volcano example and this manipulation experiment and yeah, are there other natural experiments you could bring to this synergistic additive framework? Because I know that there's been other work on like temperature manipulation experiments really not giving the same kinds of responses as temperature change over time.
Yeah. Yeah, I know there's other natural experiment in Iceland that's like from a vent of like elevated CO2. I'm not sure if they have done like
There's a warming one there too.
Oh, there is.
also
Okay,
just
so maybe
like
they have done
good old fashioned climate change,
Yeah,
right?
right. It's happening over time.
Right. And there are some like kind of new, like kind of cool methods with just data analysis where they're trying to like hold other spatially variable things constant in a way while trying to assess the effects of temperature change or the method I'm thinking about wouldn't work with elevated CO2 because it requires like a variety in the atmosphere. But yeah, so I think there are some other types of data we could bring to bear on this because yeah, the global change experiments are limited in many ways.
It still requires that you measured the thing that you want in the task so that you can measure it again after it's changed.
Because in a certain sense, you can get the combined effects most easily. We actually have that everywhere. It's getting the single factor experiments that we don't actually have, right?
Yeah, but it's like how could attributing it just to just warming or elevated CO2 rather
Right.
than other changes in an ecosystem is difficult too.
Right, but if like our additive effects are putting us in the wrong sign change, and the synergistic effects are, you could at least get a sense of if the total things are absolutely wrong or absolutely right.
Right. Yeah.
Question, following up on Will's point, there's all this evidence that like cations are really important. And for forest response to whatever, and also to Scott's, earlier talk about enhanced weathering being a thing we want to do in model. Is there any talk about trying to get, trying to expand biogeochemistry to include stuff like cation cycling and alkalinity and obviously that would be a huge lift, but like, is it even like on anybody's radar?
pH on the surface data set now. As far as we've gotten, so no, not that I'm aware of anyways. Yeah, that's a good question.
Should we break early? Or no?
Sure, brave the children.
Any other last?
Yeah, I think you heard about it. Okay, so if we break early, then we'll be back here at 11 o'clock for the last set of emission. it close enough?
It's pretty close.
Okay, it's close enough. All right. So first up in this session, we have Peter Lawrence.
Thanks, Kristen. So I'm actually really excited to present this. This is a body of work that we've been doing here at NCAP the last couple of years and trying to work out how we can transition from like prescriptive ways of running CSM to having more interactive and emission-driven ways of running the model. It allows a whole new bunch of science for us to do. And obviously this is a large number of co-authors here and people who've been contributing to this project. But one of the key things is trying to work out how can we use this new configuration of the model to ask questions about both historically what's been going on with like the carbon cycle, climate, but also projecting like along different scenarios. Just to quickly give you a background, we're using CSM 2.1.5, which is the default version of CSM on derecho for 2.1. It's been expanded so we can have active fires and biogenic aerosols for using the Megan model and the fire model in CLM. We have this new 4P2Z, which has 4 phytoplankton and 2 zooplankton ocean biogeochemistry in it, which is Kristen's done a lot of great work on that. We've updated the CLM5 surface data sets to be consistent with CTSM 5.3. And then what we did is when we started running the model, we realized that when you have fire and volatile organics working, the aerosol model responds in a way that sort of is very sensitive. And so if you're inconsistent with the CMIP6 prescribed aerosol precursors, then you end up with a model that cools very rapidly. So we did quite a bit of work changing the emission factors. We didn't change Megan and we didn't change the fire model. It was just how those two, the emissions from that ended up going to the into the aerosol model, so MAM4. From that, we have 5 historical ensemble members, which we took from a pre-industrial spin-up. So we sort of branch off at 130, 135, 140, 145, 150 years into this pre-industrial spin-up. And then we're looking at, this is what the session is going to be a little bit about, is the highly optimistic projections ensemble, HOPE, which is a project we're running here, which is comparing SSP 119, which is the only 1.5 degree warming scenario in the CMIP6 project, against 245, which is around about 2.5 degrees of warming, versus 370, which is like just over 4 degrees of warming. So each of those ensemble members from these different scenarios start at the end of the historical. And we're also using the same framework for the Community Climate Intervention Strategies project, which is a project where we're exploring carbon dioxide removal and solar radiation modification. One of the nice things about the HOPE ensemble was it allowed us to explore the model in the CMIP space to see how effectively we could reproduce the model. Because the talk's short, I'm not going to go into a lot of details here, but I just wanted to get an idea of the complexity of what the model's doing. You know, once you have all these different types of activities happening on the land surface, and then you have like the fires, the volatile organics, and you have CO2 all cycling, the model allows you to see this integrated sort of way the model responds to human decisions and human activities. We've got the fisheries in there because that's one of the nice things about using the 4P2Z model is we can have the feisty model can be run off this, so we can look at fishery impacts as well. Okay, one of the first things we want to do is really assess how this model runs compared to the LENS project. So we have LENS here, and what I've got here is LENS, which is the smooth biomass burning ensemble members only, and I'm using 5 members from HOPE and CCIS versus 5 members from the LENS project. Here we have had crew just as like a surface data set to look at the temperature change over that time. And above the 2 plots on the left is the interactive emission-driven simulation versus the LENS 2. And you can see over the historical period, we have similar warming sort of spatially distributed, slightly more warming in the Arctic for the emission-driven scenario. But one of the key things is that the model is actually cooler in emission-driven space in 1850, and it follows more closely to the HAD crew time series exploring going forward. There is slightly more warming in the emission-driven run, but it's very close. So if we look at the differences between emission-driven simulations and the LENS 2 at the beginning, like so 1850 at the beginning of the historical period, and then in the current day at the end of the historical period, we can see that the emission-driven run ends up being quite a lot cooler in the southern hemisphere, especially like down at high latitudes in the Southern Ocean. And then we also see this cooling across the central Atlantic and the central Pacific. One of the other things that's sort of interesting to see is when you run the model in this emission-driven space, you can track out the CO2, the observed CO2 record really nicely. The dashed purple line is when we use raw emissions and raw land use. So we sort of have this diversion around about 1945. For these simulations we're doing here, we really wanted to have 2014 CO2 spot on because we're doing it for carbon dioxide removal and other things. So we went to the Global Carbon Project and took out there's a term in the Global Carbon Project, which is the imbalance, because if you add up all of the terms in the Global Carbon Project, they don't reproduce the CO2 record. So we're just taking that out. So we have this, let's see if I can get this to work. Yeah. So just here, this purple line, we bring it down to this green line, but it's a pretty small difference in terms of CO2 trajectory. One of the other things is with the interactive aerosols, which is over on the right-hand panel here, the blue being lens, the green being the interactive emission-driven run, we end up with slightly lower aerosol burdens globally. What's interesting is even though the aerosol burdens are lower, spatially there are important things happening. So we end up with much higher volatile organics coming out of the Amazon, which sort of come out over here through the Central Pacific. And this corresponds to this area of cooling over the Central Pacific here. Okay. We can also look out to 2100 along the SSP 370 pathway in an emission-driven space versus the Lens 2 extension. And we can see that we end up slightly cooler in the emission-driven run than we do in the prescribed CO2 prescribed aerosol simulation. But we're starting cooler and we're ending cooler. So when we do this, if we overlay on top of each other, we can see that they're basically following each other very closely. And if we just look at the deltas from 1850, they basically lie on top of each other. Okay, so getting to the aerosol component of it, and what I've done here is compared Lens 2 prescribed aerosol values for black carbon, primary organic matter, sulfates, and secondary organic matter. And you can see for the fire component, which is really coming out in the black carbon, the primary organics, and the sulfates, we do a really good job. We retract like what's coming from CMIP6 all the way out. What is sort of I guess you can see this here, right down here on the, okay, so over here, this area here, you can see that the Megan model responds very strongly to temperature. So we're out through SSP 370, and we're seeing this large ramp up in volatile organics that we don't get from the CMIP6 from the CMIP6 forcing data sets. Okay, so if we go through the literature and have a look through, is that expected? Is that something that we would want to have in the model that wasn't previously there? And the answer is, yeah, there are a couple, there's observational studies showing this, and there's also the 1% ramping CMIP6 simulations where they had interactive volatile organics in these different models. And they all show this really strong response. So you've got temperature in the blue there versus the amount of volatile organics being produced in the red. And you can see that there's this very strong temperature response within the models when they are in this sort of volatile organic explicit configuration. Okay, so going beyond temperature, going beyond aerosols, the model has some responses in terms of precipitation as well. And that's something you'd kind of expect considering that this is a precursor to interactions for clouds and then rainfall. So if we look at this plot down the bottom here, okay, so the plot down the bottom here, we can see that with interactive aerosols, this green line here, we actually are quite a lot lower in 1850, well, quite a lot lower in 1850 than like the prescribed CO2 prescribed aerosols. We also have this smooth sort of slow ramping up. Interestingly, in Lens 2, there's this drop in precipitation after that 1960. But we see that there's this difference here. And a lot of this difference between the two models, between the two configurations of models in 1850 is here through this region where the volatile organics are coming out from the Amazon. So we can see once we get to if we go through to like current day, that difference actually gets a lot smaller. The model's warming up. There's less impact across that region. If we go to the global precipitation climatology project, this here, we actually can see that the model itself actually has in both configurations big high precipitation biases in this region here. Whether you believe GPCPE or not, we feel like the model differences are much smaller than the differences to the sort of observational products. And then going out to 2100 along the SSP 370, we see that again, this region here through the Central Pacific is where we have the lower precipitation in the emission-driven runs than we do in the prescribed model runs. Okay, so moving on to the carbon cycle, and one of the things was we did this fun. There was a fun bug that was sort of like there was some logical error in the fun code about when to apply pixels, and so that actually means that our model with this new fun fix has slightly higher MPP through the whole project, a whole time series, both through the historical and the SSP, and that results in higher total global ecosystem carbon and vegetation carbon, soil carbon, and I guess soil carbon as well. Because we have a higher standing carbon, we end up with more land use because the same land use change has more carbon in the standing forest when it happens. So we do end up with more land use occurring in that point. Wood harvest, because it's actually prescribed in the amount of carbon we want to take out, didn't have a real impact. Okay, now we've got this model and we're sort of feeling like it works within that lens framework. We can understand what's going on. It allows us to start exploring spaces that we couldn't previously explore. So the SSP 119, there was no forcing data sets for this in terms of CMIP6 concentration-driven runs. So what we can do is that we can now run the model with the emissions from SSP 119 and see how the model responds. Can we get this 1.5 degrees of warming versus the 2.5 degrees of warming in SSP 245 or the 4 degrees in 370? A lot of this is like there are a lot of mitigation and intervention type activities. We want to explore whether we can get them to work inside CSM with a responsive carbon cycle and responsive aerosols. So just quickly, what does SSP 119 look like in terms of fossil fuel emissions? This dark blue line is like we rapidly decrease in emissions going through to around about 2035 where we go negative, and then we're drawing carbon down through direct air capture and bioenergy carbon capture and storage. We also have this large-scale reforestation happening here. And if you compare that to 245, which is, we have this peak around about 2050 in terms of emissions, and then we slowly decline. We don't actually get to net zero, but we decline, so we've got low emissions there, versus 370, which is this continuing ramp up of emissions going out to 2100. You can see that the crop space. So we put all this in the model, and we basically end up, so this bottom right plot here shows the atmospheric CO2 from the dotted lines, which is the prescribed CMIP concentrations, versus what is coming out of the model in full emission-driven space. We pretty much hit 370 straight on. 245, we're just a little bit low for 245. And then 119, which hasn't actually been previously exercised, we sort of peak in terms of CO2 concentrations around about 2025, and then we go down this rapid decline, and we end up below current day at the end of 2100. You can see here in the temperature responses, we have all three scenarios run out for the first 15 to 20 years along the same trajectory, and then the CO2 removal ends up kicking in around about 2035, and we start having rapid cooling through the end of the 21st century. Again, we have the 245, which ends up with around about 2.5 degrees of warming, and SSP 370, which ends up around 4 degrees of warming. Okay, thanks. Okay, so one of the interesting things, if we look at where those temperature responses are happening, is we can see that for SSP 119, when we're returning back to a temperature that's kind of current day-like, but we have this large-scale decrease in the AMOC circulation. So we end up with large-scale cooling here in the North Atlantic. And we see this AMOC shutdown in all the scenarios, but it's really pronounced here where we're actually getting cooling through the period of time. In fact, we end up with cooling in the North Atlantic it's much larger than the historical warming, so it's cooler there than 1850. So the question is what's happening here? We can see that all three of the scenarios, the blue line here is the 119, they all have this collapse in AMOC, and it takes a long time for AMOC to turn around once you start cooling, get to this sort of cooling phase. And that's consistent across the CMIP6 archive. You can see this is a paper where they showed the decrease across all scenarios of AMOC, and the response of the decrease in AMOC is really relative to the size of AMOC. Quickly, pre-SIP, we end up having decreases, so we have a shift in the ITCZ across all of these scenarios. The stronger the scenario, the further it shifted south, and the stronger the increase in the southern Pacific, in the central southern Pacific. We see decreases in the Amazon across all of these time series. Okay, carbon cycle. So this is really interesting in that we're doing large-scale reforestation in SSP 119. And so if you look at the land flux here, we see that drawdown in carbon, so negative as a drawdown from the atmosphere, is really strong. But once the CO2 starts like going down, this sink that we had here like starts reversing, and we end up going back to the point where we're almost losing some carbon here at the end of the time. And the ocean is actually outgassing at the very end of this period on SSP 119. There we can have a look at the GPP and MPP. They both follow along the CO2 trajectory almost exactly. Okay, so what's happening with this carbon cycle, total ecosystem carbon? We see that the CO2 fertilization and land use are interacting with each other. So we have much higher MPP in 370 than we do in 119. That means that our total vegetation carbon and our ecosystem carbon is actually going to be lower in 119 than it is in 245 and 370. Okay, I'm just going to leave it here. This is work we're doing with climate interventions. This is work that's ongoing, looking at solar radiation modification, land CDR, and marine CDR, looking at different effects of different activities. I'm just going to leave it on this last slide, which are the ongoing projects we're using the interactive mission-driven simulations for. So we've got CMIP7, fast track. Can we look at the new drivers? Can we use CSM 215 as like a case study for that? Flat 10 simulations, which we did with Charlie and others, that we're looking at what happens in idealized emission space. And we're also using this model for TIPMIP, or the tipping points efforts. And with that, I'll turn it over to
Maybe time for one question. Keith, yes.
It's not a question as much as a comment, but in your scenario runs, when you're comparing the emission-driven model to the concentrations coming out of the IAMs, I think it's worth saying that the IAMs are not truth. No. They are a different model. So the way you phrased it of we're right on track. Well, right. That just means you're agreeing with another model.
Absolutely.
And whether you're high or low or right on track just means that the models agree or disagree, which is not necessarily a target that you should be aiming for.
And maybe like what I was trying to get is the fact that CO2 is going to be consistent between the large ensemble and also the emission-driven run. So CO2 will be consistent, maybe consistent rather than on track. That's a good point.
That's not good either.
Yeah,
necessarily.
Not necessarily.
That's not a good result. That's just.
It's a result.
It just shouldn't be applied if that's the case. That's the point.
Okay. Well, I think if it were wildly different, then it would be hard to interpret like the climate response. But yeah.
If it was wildly different, it might mean the carbon cycle is really, really important. Yeah. So I think that it would be okay too. Anyway.
Yeah. The IAM is really bad.
Yeah, maybe the IAM is just really good.
Right. Thanks, Peter. Next 12 step. Great. Next up, we have a bunch of comments. More about mission driven run. I'm just gonna hold this up.
Can you hear me okay? Oh, yeah, you can. Okay, so I'm going to show you, I guess, some second results from CSM Home because you just saw some first results, mostly focusing on the carbon cycle part of this, yeah? I can't hold it. Okay. Okay, sorry, I violated the rules. I want to acknowledge that none of this work would have been possible without Peter, without Dave pushing behind the scenes to get it out, and without the scientific steering committee of CSM who got behind this idea when I presented it like a year and a half ago. And also all of you in this room in some way probably have contributed to promoting the idea of having CSM Hope come through. So what is CSM Hope? As Peter just explained, CSM Hope is a set of fully coupled emissions-driven simulations of CESM2. And the idea that I pitched to the SSC a while back was that we had done already with CESM a number of large ensemble simulations using sort of high-end emission scenarios, right? SSP 585 and SSP 370, but we hadn't yet explored using CSM what would happen in some of these more optimistic emission projection scenarios, right? So something like the teal line or the blue line on this graphic, where we get to real net negative global emissions somewhere in this century. Wouldn't it be interesting to look at how the climate system and how its variability responds to such a drastic reduction in emissions, recognizing, of course, that it's not probable, especially now, that we're going to follow any of these emission trajectories, but it's also worth exploring what and how the Earth system might change in response to that. And we named it CESM Hope, Highly Optimistic Projection Ensembles. My husband came up with that acronym. I think it's perfect right now because don't we all need a little bit of hope right now? So that's the idea. And because the atmospheric CO2 in CESM Hope simulations is not prescribed as it has been done in the past, it is emissions based, which is what was called for in the CMIP7 literature. We're actually predicting the atmospheric CO2 concentration as a result of the anthropogenic emissions of carbon, plus the interactions of the atmospheric carbon with the fluxes of carbon dioxide between the ocean and the atmosphere and the terrestrial biosphere and the atmosphere. So what I'm showing you here in this movie that I made, I know it's not perfect looking, but I made it in MATLAB. This is the mixing ratio of CO2 in the lowest level of the atmosphere from January of 2000 to December of 2014. There's no color bar on here because I've taken out the global mean value from every data point so that you can see the seasonal variation in the emissions. You can see the seasonal breathing of the Northern Hemisphere in this image. And so you can see sort of the point sources of the emissions imprinting on the atmospheric CO2 concentration locally. And so you see there's a lot of spatial and temporal variability in the mixing ratio of atmospheric CO2. And that's all borne out because we're prognostically predicting the atmospheric CO2 concentration. So I've started to do a little bit of validation on the CSM Hope output using the historical ensemble of simulations that Peter just introduced. And just as an example here, this is a still image showing the mixing ratio of CO2 in the lowest level of the atmosphere everywhere in the very last month of the historical simulation. This is December of 2014. And so you can see the patterns associated with emissions and the breathing of the biosphere. And then I've drawn out two places where we have real world data from the NOAA Flask network. One on the right is from ALERT and on the left from Mauna Loa. And plotted here is the seasonal cycle anomalies associated with the mixing ratio of CO2 that's measured at the flasks in blue and from the 5 ensemble members in purple. And this is just for the year 2014, just as an example. And you can see that in both cases, at both places, the amplitude of the seasonality is spot on as compared to the Flask data. And for ALERT, the phasing is also spot on, but for Mauna Loa, there's a slight shift in the phasing here. And those of you who are sticking around for the tutorial this afternoon, I've just learned that 45 people signed up for it, so that's exciting. I don't see 45 people in this room, so I'm not sure who all signed up, but I think you'll have an opportunity to do additional validation exercises with atmospheric CO2 and CESM Hope. And if you do, I would encourage you to look at the South Pole because it doesn't look nearly as good as the two panels that I chose to select for this plot. So there's something hidden in there that you should take a look at. Peter's also demonstrated that the CO2 fluxes from the CSM Hope historical simulation match those from the global carbon budget, but here's another illustration of that. So on the left, I'm showing the globally integrated flux of CO2 between the terrestrial biosphere and the atmosphere from 1850 projected out to 2100, and on the right from the ocean to the atmosphere. And the gray lines in both of these are the 5 historical ensemble members of CESM HOPE. And the black lines are the global carbon budget estimates of the globally integrated flux. And you can see that they match not only in terms of the mean flux, but also in terms of the interannual variability in that flux. So we're doing a pretty good job of matching what we have observed. And I recognize a lot of this isn't real observations. It's just a reconstruction of what we think might have happened. Also shown on this plot is something that Peter illustrated in one of his previous plots, but I do want to call your attention to it again, is that when we use CESM HOPE to project what the future might look like in terms of the globally integrated carbon fluxes for the ocean and the terrestrial biosphere, in the ocean there's a very clear and clean separation in terms of what the CO2 flux does. And uniquely, we now have SSP 119, and we can see that under SSP 119, the ocean sink reverses course pretty much right away. As soon as you slow the rate at which you emit carbon into the atmosphere, the ocean takes up less carbon, such that by the end of the century, all 5 of the CESM HOPE ensemble members predict that the ocean is now degassing carbon dioxide into the atmosphere. So you have to imagine that the ocean has been taking up all of this extra carbon and it's holding it. And then if you lower the atmospheric CO2 enough, it's going to start coming back out into the atmosphere. And that's, I refer to that as the burp. You see the burp happening here, right, in the ocean. It's really distinct. On land, it's much more difficult because there's so much internal variability in the system that it's difficult to tease apart the different emission scenarios here and what's happening in the future. But you do see at the end of the century, there are a few ensemble members where for a few years, there is a net source of CO2 to the atmosphere globally integrated. Because we're generating an ensemble of simulations, each one of those ensemble members has different phasing of internal variability. And indeed, all 5 ensemble members of CESM HOPE have different phasing of the ENSO index. Here, I calculated a Nino 3.4 index for the 5 ensemble members from 1984 to 2014. And the interaction of El Nino with the carbon fluxes looks like we might expect it to look based on what we know from previous model simulations and also from observations. So on the top right, I've taken just ensemble member number 1 from 1984 to 2014 and regressed the local CO2 flux anomalies onto the ENSO index. And so what you see wherever you see red up there is when there's a positive phase of ENSO or an El Nino event, there's a degassing of CO2 from that region. So you see the Amazon is very red. It's hard to see because there's very little land, but Southeast Asia and Indonesia is also very red. So this corresponds with what we might expect to happen in the real world. On the bottom, you also see the ocean flux response to ENSO in CESM HOPE. And just as you might expect, right in the central equatorial Pacific, you see a lot of bright red. So anomalous degassing of carbon dioxide from the ocean in those regions. And this, of course, varies from model to model, but it more or less looks like all the other models in terms of its response to ENSO. So I think that that's very promising. What I've started to look at more recently, and by more recently, I mean last night, is can we actually see the emissions reductions in the atmospheric mixing ratio of CO2 or in the atmospheric CO2 concentration? If we follow SSP 119, when can we notice the emissions reductions in the atmospheric CO2 record? And we can do this uniquely with CESM HOPE because it's an emissions-based set of simulations. So what you're looking at here is just at Niwot Ridge, which is one of the sites just right over there, the model estimated mixing ratio of CO2 at that location. So I've subsampled the model right at the grid cell that corresponds to Niwot Ridge. And here we're looking at the 5 ensemble members historically in black from CESM HOPE from 2010 to 2015, and then the projections of what that mixing ratio might look like in the model under SSP 245 and SSP 119. And it's very subtle, right? Over the period from 2015 to 2025, we are reducing globally the emissions and on a large scale, and yet it's really hard to tell them apart. There's so much internal variability in the system that they overlap, right? The ensemble members overlap. And we only have 5 ensemble members. Imagine if we had 100 like some of these large ensembles, it would be really hard to tell it apart. So locally, it would be really hard to detect this large scale global reduction in emissions if we were looking for it in the atmospheric CO2 mixing ratio. But if I average 12 of the most commonly sampled flask sites across the entire globe, I can start to see a cleaner separation of these 2 lines. So here, over the same period of time, I've averaged the data subsampled from where 12 different flask sites would be. And you can see that the internal variability is damped down when you average across different spatial scales. And we know this from the work of Hawkins and Sutton and many others, but it shows up here in the atmospheric CO2 mixing ratio record, or the anticipated projected record if we were to cut our emissions. So if we're looking for the fingerprint of the emissions reduction, we shouldn't just look at one spot, right? We should really look at across the globe what's happening and see if we can see that, especially if we're having global emissions reductions. Okay, so but what would happen in a world where we don't have the counterfactual simulation? We don't have SSP 4.5 to compare it to. Would you be able, for example, in this record, to say, yep, I see the emissions reduction? It would be pretty hard, right? Because it looks just kind of like it keeps on going up and keeps on going up. Where would you look, and this is for the global 12 sites, to see that emissions reduction? So I've started to tease this apart. I made this plot last night, 11 o'clock. So the way that I think we can see this emissions reduction is by looking at the change in the growth rate of atmospheric CO2. So instead of looking at monthly mean, which is in the top plot, I've now annualized all of the projections. So on the bottom, it's annual mean, which makes it easier just from the get-go because there's less variability. And so the blue line is the annual mean XCO2 averaged over the 12 flask sites, and you see it's going up from 2015 to 2025. It's very subtle in there, but the growth rate is plotted on the right side of the y-axis there in purple, and the growth rate is indeed beginning to decline, right? So as we reduce our emissions, the growth rate declines. There's a negative slope in the growth rate, and that's our first sign that we can see the emissions reduction in the atmospheric CO2 record. But in fact, I did a back of the envelope statistical analysis calculation to figure out when would that negative trend actually emerge. And with 95% confidence, it takes until halfway through the year 2024 for us to see it. So what that suggests is that even if 10 years ago, we had started on the SSP 119 trajectory, really cut back our emissions, we would only have been able to really say confidently that we saw it in the atmosphere last year, right? So it takes a while for this signal to develop. I put this up as future work. We don't know if we're actually going to get the money to do this, but we just put in a proposal with the NASA Carbon Cycle Science. We're not sure even if we have a program manager there anymore, but we put in a proposal to develop a satellite XCO2 simulator. So the satellites that are flying up there can measure the total column or the column average CO2. And what we would like to do is see whether it is possible to detect emissions reduction both locally and globally using a satellite. So we're going to build in a hypothetical XCO2 simulator, and we're going to fly it around in the emissions-driven version of CESM HOPE to see what signals it produces. And then we're going to fiddle around, if we get the money, with what happens if we impose CDR in a particular location. What would that look like for a satellite that was flying in the model system? So this is satellite XCO2, and this is if we were going to subsample the model like the satellite would. And we would do this at runtime, so online. So to conclude, I hope I've convinced you that emissions-driven historical simulations of CESM HOPE generate a somewhat realistic representation of the present-day carbon cycle. Under extreme reductions in emissions, CESM HOPE predicts that the ocean will become a source of CO2 to the atmosphere by the end of this century. And the fingerprint of global emissions reductions can be detected, but only if we look at the declining growth rate of the mixing ratio of CO2 in the atmosphere from the global class network, but it would take at least a decade for us to be able to see that. Thanks so much for your attention.
Thank you, Nikki. Do you have any questions? Yes.
I need a mic or the room's big? Okay, sorry. Thanks, Nikki. I mean, I think this is going to be a really valuable resource to, mine for lots of different questions. I guess one comment, I think the biggest challenge is not going to be detection, but attribution. And my somewhat pessimistic mind, I think what would happen is we would do everything for SSP 1.9, reduce emissions, CDR, and then see if it would keep going up just as fast as it had, previously. And we would be left wondering if that was because the oceans or the land were doing something we didn't understand, or people were not, reporting their emissions accurately. And so then how would you separate?
Yeah, so that's where the HOPE ensembles actually can be very helpful, right? So attribution exercises can be done with these idealistic ensembles, right? And so you can say like, yeah, this happened. And if I have a counterfactual simulation where this didn't happen, now I know that I can attribute the change to the change in the emission. So we can do those kinds of attribution studies with CESM HOPE, which is pretty cool.
I was going to respond to Brent. It's worse than that.
because once you do the emissions reductions, you're reducing all the aerosols associated with it. So 119 actually warms faster than 245 or 370 for the first 15 years. So you're clearing up the atmosphere and you get this strong warming response. So it's very hard. How do you communicate that as like to a decision maker? Oh, well, if you do this emission reduction and you're taking all these aerosols out, you actually end up with a warmer planet. So that's where we're sort of, I guess.
Temporarily.
Yeah, temporarily. I mean, once you get out far enough, sure. But most decision making isn't happening on a 20-year time span. It's more election cycles and things like that.
Yeah, and so, I mean, how do you, like, from this attribution perspective, given that the models show very different lags in terms of the response to changing emissions in terms of the carbon cycle uptakes, like, you know, and here you're just using one model, which has one time scale associated, or one set of time scales associated with it, which is unknown and biased, right? How do we deal with that piece of the uncertainty?
Great question. We'd have to have more months.
Or more, or ensemble of simulations with CSM with different character, right, of the carbon cycle, which is the idea that Abby and I and some we're trying to push for season 3.
So next up, we have Abby Swan.
Okay, great. Thank you. So I'm going to talk about looking specifically at land carbon sinks, and I'm going to look under zero emissions and decarbonization scenarios. These are going to be more idealized than the HOPE experiments. I put just Charlie Coven and Ben Sanderson on here because I'm going to show some work that Ben has led and Charlie's been involved, but there are lots of contributors to this flat 10 myth that has happened. Many models have participated. Peter ran the CESM runs, so thanks to all of them as well. And once I actually share what I've done and talk to them more about it, I'll have many more names to put on here to thank. Okay, and this is a preview of what we're going to see for land carbon uptake. So I wanted to start by pointing out that emissions-driven simulations show a spread in atmospheric CO2. This is looking across models in CMIP6. There is a limited number of models that did these simulations, about 12 for CMIP6. This is showing the CO2 concentration in the atmosphere under RCP 8.5. And there's a spread of about 250 parts per million in the atmosphere across different models. CMIP7 will have more emissions-driven simulations. That's the idea. Groups are being asked to run their main simulations as emissions-driven. So this carbon cycle uncertainty will be present in many of the future projections coming out of CMIP7, and it's really important for us to try to understand that better. A lot of the across-model spread in the CO2 is coming from fluxes of carbon from land. I've scaled these two plots to the same. Oh, it got a little messed up. I'm sorry. They are the same size. They're not next to each other, or they're similar in size. Okay, just believe me, the ocean fluxes or distribution across the models is much smaller than it is across land. And so a lot of the uncertainty contributing to this is coming from differences in how land carbon is operating. It's just not to say those ocean fluxes are not important and the differences between models are not important, but we're getting a lot of this distribution from what's happening on land. So we're going to concentrate on land fluxes here. And this is just to remind you that this spread in atmospheric CO2 that we get across these models running interactive carbon cycles results in a spread of temperature as well. And so we do not necessarily expect that the emissions-driven simulations will have the same distribution of temperature projections, because there could be additional contributions from the radiative forcing of different CO2, as well as other confounding factors. So I'm going to discuss today a very idealized set of experiments to try to look at the relationship between, designed to look at the relationship between emissions and
carbon cycle behavior and temperature. And so these are the flat 10 experiments. They're part of the fast track for CMIP7, meaning the experiments that are being requested to be completed on the timeline to be included in the next IPCC report. The emissions look like this. They are, let's see, pointer. Oh, okay. So the emissions are approximately like fossil fuel emissions today at 10 petagrams of carbon per year for 100 years. So that gets you to 1,000 petagrams of cumulative emissions, which is what we see over here in the blue line. And then we have an experiment in orange where the emissions go immediately to zero. So at zero emissions that happens instantaneously, then continued at zero. And a separate scenario where the emissions are ramped down more slowly, but this very idealized way where we go into full carbon dioxide removal. But we also have a slower decline towards net zero emissions in this first part of that experiment. And so we're going to look at how carbon cycles behave, land carbon behaves in these simulations. And so similar to what we see in the HOPE experiments, the land carbon sink increases, well, in all the experiments, land carbon sink increases while emissions are increasing. This is due to CO2 fertilization, higher productivity with warming, et cetera. But we have a large spread across the models here. So this is just going up to the time of net zero, so the emissions phase, and we see carbon on cumulative land carbon sink is increasing, but we've got a pretty large spread across models. If we go now to the zero emissions time frame, so emissions go to zero at this point at 100, and then there's no more emissions happening at all. We're seeing basically the result of the land and the ocean carbon sinks, taking carbon out of the atmosphere. And so how does the land sink respond? It's kind of flat in some models, and in some models, especially the ones that had weaker land sinks to begin with, we see those land sinks turn over and become sources. There's this large spread and difference in how those carbon cycles are behaving. If we look at the experiment where carbon declines more gradually and is then removed, we can look at the time at which land sink peaks, right? As you start to decline emissions, but you don't reduce them immediately to zero, when does peak land sink occur? When does land sink start to decline? And eventually, when would it reach zero? And we can see that the timing of that peak land sink also varies quite a bit across models, and it's related also with the initial sink strength. So we wanted to also understand how this projects into some key climate metrics, which is really one of the main strengths of this experimental design, is that it makes a very clean way to calculate two key climate metrics. The first one is the transient climate response to emissions. This is a plot from the last IPCC report just showing that if you plot cumulative emissions on the x-axis and warming on the y-axis, you get this pretty linear relationship across both the historical record and many of these future scenarios, saying it's a little bit scenario independent. It's just related to cumulative emissions. This is a bit of a coincidence of processes that we have this linear relationship, but it seems to be holding in models. A second climate metric that describes the response of temperature to emissions is the zero emissions commitment. And that over here is showing the time after you reach net zero. So imagine we're emitting and then our cumulative emissions stop rising. We go to zero emissions every year. How much temperature change do you get in time? And you can see there's a wide spread across models. The average in the last IPCC was stated to be zero with a range of plus minus 0.3 at 50 years after net zero. So these are two key metrics that describe the behavior of the evolution of temperature following emissions reduction, emissions going to zero. So what does this look like in the flat 10 MIP ensemble? Well, here we have the TCREs. So we have years, a 10 petagram per year emission going to 100 years here, and this is the global mean surface temperature response. It's smoothed out in the more solid lines there, and so you can see there's some spread in the TCRE would be the slope of this line, and so you can see it's different across the models. This is some combination of carbon sink processes as well as physical climate responses, rate of heat uptake by the ocean, et cetera. We can look also at the ZEC, and we see similar to what we saw in CMIP6, which is that we have quite a variability across models, some models, and so this is starting from zero emissions here. So the previous models were assessed at year 50 here in the middle, and so they were assessed as zero as the average. We can also see we have some models with positive ZEC 50s and some models with negative ZEC 50s. So there's We don't understand yet, I think, what is controlling that in these models, but that's part of the goal of this exercise, is to figure out what determines what ZEC is. I think we have a little bit better idea for TCRE. If I move that same TCRE plot from flat 10 MIP here on the left into a bigger y-axis, and we can compare it to past ensemble of carbon cycle coupled simulations that was done for CMIP3 in the Hadley Center. They did a perturbed parameter ensemble with land changes, and they get a spread. This isn't exactly the same era of models, but they're getting a spread that's quite large, which suggests that uncertainty in what the carbon cycle is doing on land could contribute substantially on top of this distribution of spread across models. Okay, so let's dig a little bit into the vegetation carbon. I'm not going to have a whole lot of insight here, mostly just tell you the models are doing things very differently, and I have a lot of work, many of us have a lot of work to understand why. But just to give you a glimpse of what it looks like, during the emissions phase, when we're putting carbon into the atmosphere, it accumulates on land. It has a different, this is a zonal plot, so with latitude on the y-axis, and we have different locations of carbon uptake. As we go to zero emissions, temperatures stay hot, CO2 will start declining. We can see carbon uptake by the land continues for a while in some models, but does start to weaken in other places. You can see it weakening in the tropics. If we look instead at the case where carbon dioxide removal is occurring, emissions reduce more gradually. In this particular model, we end up with less carbon on land at the end following this carbon dioxide removal. But this pattern is not consistent across models. So that was showing you the bottom model previously, which has a big high latitude. Actually, these are two other ones, but this is the same one. So big high latitude sink and a small tropical sink. Conversely, CESM here on the top row has a really large tropical sink. So really different distributions of where the carbon is going into land, which would also relate to the processes that are important. So I've plotted all of them here on a zonal mean, and I think this is probably too much to digest, but I'll just point out a couple of features. This is the carbon change after emissions phase. So we've had stuck 1,000 petagrams of carbon into the atmosphere of cumulative emissions. Some models show a large high latitude sink, other models show a large tropical sink. Some differences there. What changes after we go to net zero and we stay at zero emissions for 150 or 200 years, we see that the high latitude remains a sink in some models, but not in others. And the tropical sink is completely lost and becomes a source in some models, but not others. If we look at the reversibility, so how much carbon is left after we have removed all of the cumulative emissions, we can see that some models are not very reversible. They either contain a lot more carbon on land or they've lost that carbon from land, and other models have smaller change relative to the beginning. We can also look at the differences in where that carbon is located. So on the top here, I have CESM and the bottom GFDL. These x-axes here are showing the amount of carbon, the total line, and then divided into soil, vegetation, and litter. Notice the scale on CESM goes to 60, but it only goes to 15 for GFDL. GFDL has far less soil carbon to start with compared to CESM. And then if we look at how much carbon is gained during the emissions phase, you can see the GFDL gains almost no soil carbon. CESM gains a lot of vegetation carbon and some soil carbon. So really different behavior of what's going on with land carbon cycling. So there are many remaining questions, and I'm not sure I have any real take-home points to give you in terms of what we've learned here yet, other than a lot of questions. What is controlling these differences in the land sink? What is causing these variations in the location? How does this location of the land sink and source impact TCRE and ZEC? And so I'm sort of at this point of like models are different, and I want to move to why the models are different, but need to think more about that. This is showing that that green plot that I showed you earlier across the models, just to show you the really different character of what they're doing, why the carbon is going where it's going. So this is just the beginning of ongoing work to figure out why this is happening. And then, as Dave alluded to, I'm very interested in trying to run multiple ensemble members with different assumptions about land. So if we take CESM and we make it have higher photosynthesis or lower photosynthesis or different behavior of soil carbon pools, how much does that vary the behavior of CESM, and how does that look in the context of this multi-model ensemble? And then it'd be very interesting to also bring observations to that problem to see if we can try to understand their current behavior and think about what that means for the future. So lots of ideas about what to do in the future and lots to figure out. I hope that some of you can come and think more about what we can learn and how we can learn it about land carbon in the afternoon tutorial as well. Thanks.
All right, questions for Abby? I'm sorry.
I'm okay with that.
You can actually,
Okay.
the ceiling mine is.
So I have a couple of questions for you. One is about the early slides where you show the plateauing of the emission of the carbon sink. There's no fluctuation. So do you know what happens if you were to continue the experiment for a couple of 100 years? Like, it's not like the model could just take in as much carbon as possible, right? There must be some saturation at some point. And
Yeah,
you
I
know,
think these are questions, right? Like, why do some of the models saturate and some of them don't? And yeah, so I think that's a cumulative land sink plot as well, right? So when do they start losing carbon versus when are they taking in more carbon? But I think we see the vegetation carbon increases really a lot in CESM and many of the models. And is that reasonable, or should it be saturating sooner is a big question.
and my second question is, do you know if at the state of the modeling that we have right now, is there a big component of carbon sink or emission that is missing in the land model to refine the results? I have no idea. So,
A big component. I'm not sure I said it.
is there any mechanism that is like really missing in the models right now that could capture like or refine the results that we have right now based on our understanding?
That's the question broadly to the land community. I think there's a lot of uncertainties. I'm sure there's missing mechanisms. Is there some, critical single mechanism that's missing is probably hard to say. But I think even just the uncertainty and what we know about the existing mechanisms would probably create a very large spread around the individual CESM ensemble member, which is something I'd really like to understand more.
Yeah, there was somebody online too.
I
so
don't know.
I think-
He wants to go first. Renato?
Oh,
Why don't you go ahead?
okay, so, a question and a comment. I went by kind of quickly, so I was just curious if this axis of variability between tropical sink and northern extratropical sink maps onto the different time responses or different things that you showed earlier. And then just a comment that, since we started doing these global scale greenhouse gas surveys in 2009 through 2018, we have really a much better handle on what the actual distribution of land sinks is between the tropics and the north. And so we can actually, start to reject some of these models. Unfortunately, it's looking like more of a sink still in the northern extratropics, which is not what CESM is showing. So I think understanding that what's driving those differences could be really key.
Yeah, and I'm definitely bringing in as many observations as possible because I feel like we're very observation limited. I don't think the observations belong directly compared to this particular experiment because it's so idealized, but that's where we bring in the whole historical period. I don't know if we should move on to the last talker.
Yeah, maybe.
Can people hold their questions for the discussion?
Yeah, there's a discussion period. Okay. So next up, we have Gretchen. Oh. Okay.
I get that pulled up. What it is.
I'm sorry?
I get that pulled up.
Okay, great.
All right. I think Thanks. So this talk is very much transitioning us into the tutorial mode. There's not a lot of new science in this talk. It's a little bit more pedantic, but atmospheric CO2 is something that doesn't often come up in these talks. So thanks to Nikki for showing us some atmospheric CO2. So the goal of this presentation is just to illustrate a little bit about what we can do when we track atmospheric CO2 and a little bit about some of the caveats for how to do it in a way that we don't avoid aliasing other types of biases into our interpretation. So this is figures from a paper by Heather Graven that came out over 10 years ago now, but in it, she's showing that the amplitude of the CO2 annual cycle is increasing over time. It's increasing more at Barrow than it is at Mauna Loa. And I think this is just a really nice example that atmospheric CO2 is something that, especially in flask or in situ observations, we can track to, and Britt might disagree, but like essentially zero analytical uncertainty, right? Like it's a very precise and through calibration, a very accurate way of diagnosing what's happening with the carbon cycle. And one of the themes when we're, sitting through all these land talks is just how much heterogeneity there is. The atmosphere integrates over a wide area. And so you can discern these patterns of behavior that can then provide insights about where we should be looking for more process level insights. So in this case, it sort of implicates that there might be more changes that are occurring further north and further south within the Northern Hemisphere. So this is an example of what fossil CO2 in one of these emission-driven runs look like. So this is just the year 2014, so the last year of the simulations. This is spatial variability in fossil fuel. The absolute numbers maybe don't matter so much, but you can see that when we emit CO2 in these emission-driven runs, we maintain spatial variability in this case, the fossil CO2 component. You can see that it's higher over Eastern United States, Western Europe, China, areas that we know there are a lot of emissions. We see that CO2 is higher in the Northern Hemisphere than in the Southern Hemisphere. And those types of variations can be useful for diagnosing fluxes. And there are ways that we can use those types of variations to, again, sort of refine our understanding of how fluxes might be changing with time. So this is an example from an old paper that I wrote where in both the observations on top and in CESM1 on the bottom, you can look at the contrast between CO2 observed or simulated at Mauna Loa and the South Pole. And you can see that that value regresses in a linear way against global emissions because those emissions are primarily released within the Northern Hemisphere. So this approach has been hypothesized that even before we have observations, we can sort of diagnose what would be the net Northern versus Southern Hemisphere uptake or release of carbon back when emissions were zero. Within CSM1, we also use some of the spatial variations in CO2 to understand how patterns might change as fossil emissions change. So here we are looking at 4 different surface sites. TAP, the site in red, is on the Korean Peninsula. And in this case, we were looking at how the contrast between CO2 at the site level compared to Mauna Loa changed as a function of Chinese emissions. And you can see that over the historical period that we've observed that there's a much faster acceleration in the contrast at this site compared to those other 3 sites in the Northern Hemisphere. And you can, in the lower 2 panels, sort of understand how that contrast would change under 2 different emission scenarios, even when active land and ocean feedbacks are included. So there's, and this is sort of, I think, what Nikki was alluding to in her talk, is that there's value to using the simulations to sort of understand where predictions would be valuable to try to disentangle some of these different types of exchange. So the fact that there's these spatial gradients in fossil emitted CO2 also enables different types of science. So here, why should a bunch of terrestrial ecologists care about these somewhat small gradients in atmospheric CO2? This is a paper by Lee et al. In 2018, where they looked at how GPP would change if there were no spatial variation in CO2. You can see that integrated GPP in the top time series might be pretty small, but on the bottom map, you can see that there are coherent regional changes in GPP. Now, it turns out a lot of these don't necessarily arise just from fossil, they also arise from interaction with land CO2. But the spatial distribution of CO2 in the atmosphere can lead to different local to regional fertilization feedbacks. Similarly, there's a paper, and I know even less about this paper, but in terms of the ocean fluxes, what they've done here is they've run a model for the coast of California, and they've used sort of regional CO2 estimates versus more highly spatially variable estimates constrained by observations to show that if you account for locally high PCO2 due to anthropogenic activity in California, you can sort of increase coastal uptake of CO2 by, anywhere between 25% and sort of a negligible amount. So there's these spatial feedbacks that can also result in ocean uptake. So tracking CO2, in a four-dimensional sense in the CESM atmosphere enables getting at some of these feedbacks. Of course, when you're tracking CO2, you can also get at spatial temporal variations due to natural fluxes. So this is again 2014. These are snapshots of what July and January look like. This is the variations in atmospheric CO2 arising from ocean fluxes. So you can see if you look at those color axes, the variations due to ocean fluxes in the atmosphere are much smaller. It's a much more smooth field and sort of a much smaller variation that's imprinted. And again, this is just the lowest model level. In land, we have a different picture. Land is the primary driver of variability, both spatially and temporally in CO2, unless you're looking at highly concentrated urban areas. But there's some weird stuff here, right? So why is CO2 so high over these tropical ecosystems where we don't expect there to be fossil emissions? And this sort of gets to a key point that I hope everyone will take away, which is that it's impossible to learn about surface fluxes from atmospheric CO2 unless you consider the imprint of atmospheric transport. So what's going on here? This is like a little bit of like atmospheric carbon 101. So when we're observing atmospheric CO2, we're looking at net fluxes. So in like over an ecosystem, there's going to be some seasonality. So you can sort of see that in that sine wave in the atmosphere. But in the atmosphere, you also have seasonal variations in vertical mixing, or you can think about that as boundary layer height. So if you look on the right-hand side, I've sort of drawn two instances where the amplitude of CO2 in the atmosphere is smaller than what you see on the left-hand side. And that can arise either due to, in the top, if the depth of vertical mixing is deeper, then whatever flux signal that's being imparted into the atmosphere will seem to have a diminished amplitude. Or in the bottom, you could just have less strong fluxes and like sort of the same depth of vertical mixing. But what actually happens in the real world is even more nefarious, which is that there's this seasonal rectification of how CO2 is emitted and taken up over vegetated surfaces and the strength of the vertical mixing. So in the summer, when it's sunny and photosynthesis is occurring, you tend to have a lot of turbulent mixing in your atmospheric boundary layer. So what that does is it essentially entrains higher CO2 air from aloft into the boundary layer, where if you're measuring at the surface, you're going to see that. In winter, when you have, maybe some net respiration or maybe just background fossil emissions being put into your boundary layer, you tend to have a lot more stable atmosphere, vertical mixing is weaker, and so you trap those emissions. And so what actually happens is across both seasons, you're sort of getting this positive bias in CO2. So that's what we're seeing in CSM. This is another example from CSM1, that same paper that I already showed a few figures from. If you look at the annual mean profile going from the South Pole all the way to the North Pole in CESM, you can see the zonal mean is the gray line, and you can see this big old bump at the tropics. And that is because tropical forests are photosynthesizing much of the year, but you have this interaction with the depth of the boundary layer that's sort of trapping CO2 at the surface. And chances are the boundary layer scheme in CAM does not look like the real world, because that sort of turbulent mixing process is something we're not super great at simulating. So you can see that sort of bias persists throughout. So that's something to take into account if you are looking at CO2. I think these are cool. So this is what happens if you look locally. Again, this is CSM1, where Keith kindly saved like hourly output. This is a tower in Wisconsin. You could compared to observations. So you can see in July down there that when you're close to the surface in the observations, you get this really huge diurnal cycle in CO2 when you're at 11 meters, which is the red trace. If you go up to 400 meters in the atmosphere, which is the purple trace, that diurnal amplitude is a lot smaller. You see all the values collapse on each other in the middle of the day when turbulence is making sort of all the levels on that tower consistent with one another. But then when you look at CESM, it's like looking at a whole nother planet, right? Like you still get that convergence in the middle of the day, but the amplitude is much smaller. And that just goes to underscore that when you're thinking about what's happening in the atmosphere, there can be a lot of compensation between potentially errors in fluxes and errors in vertical mixing. So just keep that in mind. One way that you could circumvent that is you could, instead of looking at the near surface layer, you could look at like the third model layer. So if you look at that map on the right, instead of looking at the first model layer above the surface, now we're looking at the third model layer, and you don't see those weird rectification effects over tropical forests. So there's different ways that you can try to confront that. But again, like why might we care? This is another example from that same paper by Lee et al., where they are not letting there be diurnal variations in CO2. And you can see that essentially everywhere GPP increases. And that's just due to the fact that if you allow those diurnal fluctuations in CO2 to be biogeochemically active in your model, you end up with less CO2 during the day, like photosynthesis is drawing down CO2. And so your photosynthesis rate decreases a tiny bit because your plants are awash in locally less CO2. Whereas when you don't have those diurnal effects and you're just averaging over daytime and nighttime, the plants have more CO2 concentration around them during the day. So like I said, not a whole lot of new science, but hopefully just a little bit of inspiration about why it matters to track CO2, how it can complement some of the more local scale or heterogeneous perspectives we get from looking at the land. It enables an ability to better examine these concentration-driven feedbacks within CESM. There are examples of local and regional processes that differ quantitatively when you do versus don't account for these different ways that CO2 can vary in the atmosphere. I think it opens up a lot of cool science and emission-driven scenarios. So, you know, as we've been introduced to these HOPE simulations, there's a lot that we can do to really get at what some of these are. But just the important note, it's really hard to decouple the imprint of fluxes and transport. So this is just an area where you want to proceed with caution and make sure that you are not assuming that the atmosphere is perfect. It's definitely not going to be. So we can blame somebody other than like ourselves for this one. So thank you.
Okay, great.
Gretchen, questions? Online? Oh, Abby.
bump is, because I've been wondering what the bump and the, yeah. The zonal profile.
You're welcome. It's always nice when something you take for granted can be interesting to somebody.
So that the tower site or the site in where was it, Michigan or something like that?
It was
Really bad, Wisconsin. So you're saying you think that's mostly the boundary layer? It seems like remarkably bad.
No, I think a lot of that is the fluxes too. The seasonal fluxes in CSM1 were much weaker, and I think that's something that has improved a lot in CSM2. So a lot of that is the fluxes. But you can see in the winter, for example, that there's probably also a boundary layer component, right? Because in the observations in January, you can sort of see that the red through the blue, so from 11 meters up to 250 meters, you get this collapse during the daytime. So that's the upper leftmost panel. And then at roughly 400 meters, you're still sort of outside that area that's well mixed. And in CSM, you can see you never see sort of well mixedness during January, but there's always a stratification as you sample from 11 meters up to 400 meters. So, so that I think you can, use sort of the discrepancy in January to show that there's also a problem in CAM. It's not just the fluxes in CLM. I think probably if you do the July comparison to leading order, it's probably a flux driven.
I would just add that moving up a few model levels might actually give you a reverse rectifier effect. And to really zero it out, what you want to do is take a column integral that goes up at least as high as the maximum boundary layer height.
Yeah.
And with aircraft, we can.
Yep, that's a good point. So like for those of you who use ILAM, there's an atmospheric CO2 diagnostic in ILAM, and there what we're doing is taking a vertical integral over a few model layers. And in ILAM, it's more representative and designed to be mixed with different types of models and different types of observations. So that correction has not been done precisely from site to site. But if you are doing your own analysis and trying to do your own validation, you could definitely do this in ways that are better tailored and more rigorously correct. Yeah.
Right. All right, well, we have 4 minutes for discussion. So, Charlie.
Yeah, I guess I'm interested in how these like simplified, flat 10 like mission driven scenarios can inform, or and vice versa, the scenario ones, right? Like, and because there's the two kind of very different ways of looking at this, and it seems like there's a lot of overlap in the results. Like, in Nikki and Peter's talks, right? You show this reversal of the ocean and land sinks to become sources, right? You get that in the simplified, the idealized ones too, where basically, you can calculate the land and ocean sinks as a lag response to prior emissions at some set of timescales. And I was wondering if we can, using this set of both idealized and non-idealized runs, use them to inform each other by using the idealized ones as kind of an informed null hypothesis for what fluxes you'd expect in the hope scenarios. And then further, like if that works, can we use that to sort of diagnose some things like what is the land use flux in the hope scenarios? Because, perennial problem has been, how do you actually diagnose the land use flux, right? And in conservation driven runs, we've done that with counterfactual no land use simulations. We can't really do that with emissions driven scenarios. So I wonder if we can use this kind of lag response to prior emissions, subtract that out, and if that might be a way of diagnosing land use fluxes from the scenario runs.
I guess I would just say I'm certainly thinking of the flat 10 as like trying to figure out just the carbon cycle part of it without having to think about how it's also impacting the aerosols and the land use.
Yeah.
And I hope that can be used to then do some maybe informal attribution in the more complicated scenarios.
I mean, it's sort of like a forcing versus feedback thing, right? On On the flat 10, it's purely the feedback response, whereas in the HOPE, you've got the feedback and the forcing, the land use forcing to get, and the aerosol forcing, all those other stuff. So anyway.
Can you clarify, why can't you do the counterfactual in an emission-driven scenario where you just hold land use constant, or you have no land use change?
Well, you could, but you'd be really different. It'd be a totally different thing than a concentration, because your CO2 concentration would be totally different, right? So it would be totally, you'd get a very different number.
Yes, we've been thinking about having the hierarchy of like different parts of the model turn on and off. So taking the concentration of CO2 from your baseline and then holding it constant for both with and without land use. So we can do things turned on. So we did the same things with like the fire and same thing with the volatile organics, is doing different configurations of the model and trying to do that attribution that way, rather than trying to pull it out of the full interactive model. And so, and then see how the interaction effects happen with the fully coupled model. But I think it means that you have to do a lot more simulations that way, but it does allow you to isolate different forcings out. So I guess the same way we do different configurations of the model, we do land only runs versus doing coupled model runs. We just have these different things turned on and off to do that attribution to sort it out.
You had a question earlier.
Well, I was actually just going to make a fairly obvious point, but just so everyone hears it, when Britt said that it's gradient and where the sink is from observations, I guess the aircraft, if it's coming from the mid-latitudes forests and we're simulated with a tropical, we can use the PPE to see if we can generate a configuration that puts it into the mid-latitude forests. And that would be an interesting, different number. So that's the way we're envisioning to create this ensemble, is probably more like picking and choosing rather than just picking the widest range. Maybe picking according to some sort of a feature of the system that we like to sort of test. And Lydia kind of got at that yesterday also, choosing between nutrient limited versus water limited is another axis. So really hoping, so what we really need is anybody who has a supercomputer. Anyone? So you can run the next generation large ensemble for CSM3. It seems like nobody here has a supercomputer. That per model is expensive. It's very expensive. Yeah, unfortunately, CSM3 is extremely expensive.
But I guess what I was wondering is, does it matter? So you had one model that had CNRM, ESM 3.1, had a large northern land sink and a small tropical land sink. Was it different in terms of its response to the flat 10 and zero emission? Is it, sort of like the ocean where you have things that are really different every other day and they all respond the same?
Well, I guess the other, well, I'll buy Abby some time. The other thing that I was struck by is that NOR-ESM has a much weaker tropical sink than CES have done, which is
The
shocking.
vegetation carbon CSM is kind of out of control in the tropics.
Yeah, but the same land model has a very, like, I don't know what's different about this. I have no idea what's going on there. I'm very, very curious.
CNRM and CESM otherwise have kind of similar behavior in their sort of global mean.
It's hard to really say though, because they got a different model with different temperature responses to.
This is just the land sink, but yeah.
That's why it's much easier within one model to sort of try to trace what's.
Yeah, I feel like it might be hard to build this understanding of why the models are different. And I do really want to dig in a little bit more within CESM where we have some control over choosing to force it to have slightly different functionality and try to understand what that does. And then bring it back to this context with the multi-model ensemble.
I'm wondering with like the flat 10 runs, do we know that the NOR-ESM used CLM5? Or was it a different version of CLM that they might have used? And that goes back to Charlie, maybe.
I think it's the same.
It's straight out of the box.
These are mostly CMIP6 version models that people ran.
Right.
Okay, I think we'll end it there. Let's thank all our speakers again.